So this is the first chapter of STPM Mathematics T. As you can see here, this is functions. So let's start with the functions. The next page. So we have the syllabus on top. This is for self-reading, and we start straight away. Our first subtopic here is domain and range of a function, composite functions, and then sketch the graph of simple functions, including piecewise defined functions. So first of all, let us understand relation. So we have one-to-one relation, we have many-to-one relations, one-to-many relations, and many-to-many relations. So to understand one-to-one relation, let us look at number 2, the arrow diagram. So we have one-to-one relations where one object maps to one image. Object B maps to one image, that is image D. So one object maps to one image, that is one-to-one relation. DF stands for domain of function f. So they are A and B. Range of f, C and D. The next one, we have many-to-one relation. As you can see the arrow diagram here. So what we have is, we have many objects that maps to one image. For example, object A and object B, they map to image D. Hence, this is many-to-one relation. After that, we have domains of f, domains of function f. So we have to list down the objects. They are A, B, and C. We have range of f. So pay some attention here for the range of f. Basically, they are the images with arrows that maps from the object to them. So they are D, they are E. F is not under the range because there is no arrow that maps to F. So in other words, F has no object, so it is not under the range. Okay, so we have one-to-one relation and many-to-one relations. We need to know at the same time, one-to-one relation and many-to-one relation are functions. Okay, so let me write it down over here. One-to-one relations and many-to-one relation, they are function. One-to-many relation and many-to-many relation, they are not a function. Okay, so let's move on. Number 3, graph. We have fx equal to x squared minus 4. So as you can see here, if the domains of f is equal to a set from minus 3 to 5, what is the range of f? So one of the way to find out the range of f, for me this is one of the best way to find out the range of f, is by sketching the graph. So to sketch the graph, first of all, we need to know that this is a quadratic graph. To sketch a quadratic graph, it is good to know that we have to find out turning point, x-intercept, and y-intercept. Let's start with the x-intercept. To find out x-intercept, we have to factorize x squared minus 4. We factorize it to x plus 2, x minus 2, and then when fx equal to 0, to find x-intercept, we let fx equal to 0. So x plus 2, x minus 2 equal to 0, x is equal to minus 2, x is equal to 2. These are the x-intercept. To find the y-intercept, we let x equal to 0. Then we find the fx is equal to minus 4. So this is the y-intercept. So for turning point, of course, turning point is going to be 0, -4. 0, -4, turning point. You may use completing the square or differentiation to find this. So this is just the basic quadratic graph. You can see it straight away. 0, -4 is the turning point. And as you know, when a is equal to 1, the coefficients of x squared, a is equal to 1, which is greater than 0, then the graph is a smiling face. And we have a minimum point. So hence the turning point is a minimum point. It is good to put the values of x given in the domain. So these are -3 and 5. So we have to put -3 and 5 into the functions and find out the y. So let us start with -3. We put it into the functions and we get -3 squared minus 4, then we get 5. And after that, we substitute 5 into the functions. We have 5 squared minus 4, then we get 21. So now we have to sketch the graph. Okay, so we sketch the graph to find out the range. Okay, so I will sketch the graph here. Okay, so I start from turning point 0, -4. And then like this and like that. Okay, so the turning point is 0, -4, and then just now we have the x with -3, and then the y is 5. That is the point on the left, -3 and 5. So the point on the right we have found out it is actually x equal to 5 and y equal to 21. So we have 5 and 21 as the point on the right. We also have the x-intercept. X-intercept are -2 and 2. So we can put it in the graph, -2 as well as 2. So the graph is done. We label the rest. Okay, now to find the range, we look at the lowest point of the graph, which is, you look at the blue color part. The lowest point of the graph, we look at the y value, it is -4, and the highest point is 21. So this is where we get the range. So how we write the range? If we write it in set notation, it will be like this. The range of f, y, such that y is from -4 to 21. So this is the range. Sketch the graph and find the range. So that's why the graph sketching is important here. So let us move on. The next part, revisions for graph. So we have the first one, as in A, we have y equal to mx plus c. So this is a straight line graph. So what to remember on straight line graph, so I put it here. A, y equal to mx plus c. The m stands for gradient. So if the gradient is more than 0, so basically we sketch the graph in this way. So first you have to mark the c. The c stands for y-intercept. Let's say c is here. And then if gradient is more than 0, we have to know that the graph is going up in this way. So here is y and here is x and 0. So the next one, if m is less than 0, so what should we do is, first we mark the c, the y-intercept. Then when gradient is 0, the straight line is going down in this way. Okay, so this is all about straight line. Revision for straight line, done. Now we look at B. For B, we have y equal to ax squared plus bx plus c. So what to revise on this quadratic graph? So the first thing, if a is greater than 0, the graph is a smiling face graph. If a is less than 0, it is a sad face graph. So that is the informal name for them. So of course formally we call them parabola. So number 2, you may press calculator to find the root. Press calculator for root. The roots are the x-intercept. Of course, after you press calculator, if there are integers or fractions, then you show factorization. And if the calculator shows decimal numbers for the roots, then you have to use quadratic's formula or do completing the square. And the next thing, we have to look at the c. The c in the quadratic equation is the y-intercept. Okay, so these are all about quadratic equation, and the other thing is we already have one example just now, and let's move on. Okay, so now you look at c. C is where we have y equal to ax cubed plus c. This is called the cubic function. So what to know about cubic functions? Okay, I put it here. Y equal to ax cubed plus c. So first of all, we have to know that the c is the y-intercept again. It's the y-intercept. So let's say I mark the c over here, and then if a is greater than 0, the graph will be like this. It will turn until the y-intercept in this way. It becomes flat for a while, then it go up again. So this is the power tree graph, or we call it cubic graph. So the next situation, if you have a less than 0, then the y-intercept, let's say it is there. So the graph will be like this. It moves down and become flat, then it will come down after the y-intercept. So this is the basic for cubic function. And now let's move on. The next one, D. We have y equal to a over x. We call this reciprocal function. Reciprocal functions, where x stay at the bottom. So what to know about this is, we need to know that if we have y equal to a over x, if a is greater than 0, the graph look like this. It's there in the first quadrant and the third quadrant. If a is less than 0, then you will realize that the graph stay in the second quadrant and the fourth quadrant. So this is the basic for the reciprocal graph. And we move on. E. We have y equal to fx, and then change to y equal to square root of fx. So to know how to sketch y equal to square roots of fx, so let's take a look here. I put it here, E. Y equal to fx is the graph without square root. Then from there you deduce the graph with square root. Okay, so deduce means you use your answer from what we have previously to find out the graph of this with square root. Okay, so how? Now let's see. I give you first example. If your y equal to fx is a straight line graph, it's a straight line graph like this, where the x-intercept is b, the y-intercept is a, then how to get the square root graph? Okay, remember a few things here. I'm going to say it out straight away. For a square root graph, first, we know that negative value cannot be square root. It will end up with math error if you are pressing calculator. So because of that, the effect on the graph will be like this. If there is any part of the graph that stay below the x-axis, they are negative, and hence we can't square root. Meaning that this part of graph, when it comes to square root graph, it will disappear. Okay, it will disappear. Okay, no more graph below of the x-axis. And how about the part of the graph that stay above of the x-axis? Okay, stay above of the x-axis, this part. So how is the changes over here? So we have to know that it becomes a curve. So if the straight line is going to the right, then the curve will go to the right as well. It goes to the right, something like this. It goes to the right. Okay, so the y-intercept just now, the value taken is b, and now it becomes square root a. Sorry, just now the y-intercept is a, and now it becomes square root a. Square root a, whereas the x doesn't change. So what am I trying to say here is try to observe something. When we have y equal to fx, the coordinate xy, in general I write in blue color, the coordinate xy will become x square root y. Okay, so x coordinate remain unchanged, whereas y coordinate take square root. Okay, now I give another example over here. So let's say I have a straight line. In this way, where the y-intercept is a, the x-intercept is b. Okay, so when it becomes a square root graph, so what happens is, first, the part of graph that stay below the x-axis disappear. Reason, negative value cannot square root. Second, the graph that stay above the x-axis will become a curve. So as you can see, the straight line is to the left, so it will become a curve to the left. Okay, and then the y value becomes square root a, whereas the x coordinate remain the same, remain as b. Okay, now how about quadratic graph? Let's say one more example. So I have to squeeze it here in the small little space here. So if let's say you have a quadratic graph like this, and let's say here is a, the x-intercept are b and negative b. Okay, so when it takes square root, how is the changes? Okay, so first of all, we need to know the b and the negative b will remain unchanged. And then, like what I told you before, the part of the graph that stay below the x-axis, it will disappear because negative value cannot square root. And the graph above of x-axis, it is a curve. So what is the changes here? Is it remaining as curve or how? So actually it remain as curve. Okay, so it become more round. The a just now becomes square roots of a. Okay, so this is how we sketch the square root graph. Okay, now let's move on. We already know a few techniques in graph sketching, so let's look at the next part. Number 5, other techniques in graph sketching. So we have to focus on graph sketching here, because when you know how to sketch graph, then you can find out the range of the function. So A, how to sketch modulus graph. So first we need to know modulus fx is defined in this way. Modulus fx is equal to positive fx when fx is more than or equal to 0. Modulus fx is equal to negative fx when fx is less than 0. Okay, so how we apply this concept? So let's say one example here. I give you a short example. Okay, now I pull it up here. Let's say I have modulus 2x minus 1. Okay, based on the definitions, it becomes positive fx, which is 2x minus 1. The interval 2x minus 1 more than or equal to 0. And the next one is negative 2x minus 1 when 2x minus 1 less than 0. So I follow the definition exactly and I get something like this. I simplified it. I get 2x minus 1 minus 2x plus 1. Then I simplify the interval. Okay, then we can sketch the modulus 2x minus 1 in this way. Of course, there are many ways to sketch this modulus 2x minus 1. So most people will use this way. So you see I put it in blue color first. They will sketch the graph of y equal to 2x minus 1. And after that, they label the x-axis. Here is 1 over 2, here is minus 1. So after doing so, then they change it to the modulus graph by flipping the part of graph that stay below the x-axis. They do reflection about the x-axis. So something like this may happen. So what happened is, you look at the black color graph. The graph that stay above of the x-axis remain the same, but the graph that stay below the x-axis, that will reflect about the x-axis and become like this, become a V-shaped graph. Okay, so most people will sketch modulus graph in this way. And the other thing is the y-intercept is minus 1 just now. After reflection, it become positive 1. So I mark it here. This is positive 1 now. Okay. Then what is the usage of this definition? This definition, they are trying to tell us when x is more than or equal to 1 over 2, our function is 2x minus 1, which is this graph, 2x minus 1. So this graph with positive gradient, it takes 2x minus 1. Okay, so I can just label it first. This part is y equal to 2x minus 1. Whereas this part is where the graph is reflected. As you can see, the second function here, when x less than half, the function is minus 2x plus 1, which is this straight line. So this straight line with a negative gradient, the function is y equal to minus 2x plus 1. Okay, so that is modulus function. Now let's move on. We look at 5b. 5b, as you can see, fx become fx plus a. So this is transformations. What happened is the graph will move up by a unit if a is positive, and the graph will move down by a unit if a is a negative value. So transformation happens, either the graph go up or go down. Okay, now we look at the next one. The next one is we have fx change to fx plus a. So the transformation that happens here is, if a is more than 0, then it will move to the left by a unit. For example, if you have fx plus 2, then the whole graph will move to the left by 2 units. If a is less than 0, That means if a is a negative value, then the graph will move to the right by a units. So for example, if you have fx minus 3, it means the graph moves to the right by 3 units. So these are the transformations. Now let's move on. Next one, fx become minus fx. So when the function take negative in front of it, then the whole graph will reflect about the x-axis. Next one, fx become f minus x. So when only x take negative sign, then the graph will reflect about y-axis. Next one, when fx change to a fx, that means the whole function multiply with a. So what happened is they are going through vertical stretch. So what is vertical stretch? Let's say one example. Okay, let's say one example. I put it here. Example for vertical stretch. So fx become a fx. So the basic thing that you need to know is any coordinate xy, after vertical stretch it will become xay. You see the y coordinates multiply with a, but the x coordinate remain unchanged. So let's say if I have a quadratic function like this. Okay, let's say this point is minus 4, here is 2, here is minus 2, and let's say this is, let's say 3. Okay, let's say I set up the function first. This is y equal to x squared minus 4, and let's say the point that I mark here, this point, let's say it takes 3, 5. Okay, coordinate 3, 5. Okay, so if we multiply a value to the functions, so what happened to the graph? Let's say for example, I have y equal to 2 x squared minus 4. So as you can see, I multiply 2 to the whole function just now. So it will affect the y coordinate. You just need to times 2 to the y coordinate. So this is what we call vertical stretch. So the y-intercept just now, which is minus 4, right? So now it becomes minus 8. The x-intercept, which is 2 and minus 2, it remain unchanged. X coordinate is not affected. And let's say the point just now, the 3, 5. So now it becomes 3, 10. So this is vertical stretch. And the next point that I have here is vertical press. So vertical press when a less than 1. Of course, a is a positive value, so it's greater than 0. Okay, greater than 0. So let's say for example, let's say I have, I put the example here, down here. If I have y equal to 1 over 3 x squared minus 4. So you see I multiply 1 over 3 to the whole function. So it will affect the y coordinate actually. So the graph is basically become flat compared to the original one, as all the y coordinate is divided by 3 now. So the y-intercept become minus 4 over 3, and then the 0.35 just now become 3 and 5 over 3. The x coordinate is not affected, 2 and minus 2. So you will feel like we are pressing the graph vertically. So let's see the blue arrow. We are pressing it vertically. Just now, the second graph here, this graph, you will feel like this is vertical stretch. Vertical stretch. As you can see the blue color, we are like stretching it up and down. Okay, now next one, as you can see here, fx changed to fax. Okay, so what happened here? When a is more than 1, horizontal press. horizontal press. Okay, let's say example. Okay, I use back the same functions, and now let's say I change it to, let's say from y equal to x squared minus 4, I multiply 2 to the x. Okay, so I have y equal to, okay, let's say I put in red color, y equal to 2x squared minus 4. 2x squared minus 4. So as you can see, I multiply 2 to the x. Okay, I multiply 2 to the x. Okay, so maybe I put the notes here first. If you multiply 2 to the x, okay, so I write it down here. When fx change to fax, so the effect in terms of coordinate is the coordinate xy will become x over a y. Okay, so we divide by a for the x coordinate. Okay, now how is the graph looks like? So it look like this. Okay, the y coordinate is not affected, but the x coordinate you divide by 2. So the first point to consider are the x-intercept. So the 2 and the minus 2, you divide by 2, it become 1 and minus 1. So it will become a graph that is like very thin, like this. Very thin. So here is 1 and minus 1. So the 0.35 just now, so it becomes 3 over 2/5. Okay, so the y coordinate is not affected, so the y-intercept remain as minus 4. Okay, so this is called horizontal press. You look at the blue arrow, it is something like pressing it from both sides. And the next one, the last one here, you can see when a less than 1, horizontal stretch. Of course, the other additional condition here is the a has to be positive. A is greater than 0. Okay, so let's say one example. Let's say I have y equal to, okay, so, okay, undo, let's say red color. If I have y equal to 1 over 3x squared minus 4. So as you can see, I multiply 1 over 3 to the x. So when I multiply 1 over 3 to the x, what happens? So imagine, look at this first. Multiply 1 over 3, the x coordinate, x divided by 1 over 3. X divided by 1 over 3 means 3x. So the x coordinate, you times 3. Okay, so let's consider the first thing here. The x coordinate times 3. So the graph will become very fat. The x coordinate just now, 2 and minus 2, it becomes 6 and minus 6. So as you can see here, this becomes 6 and this becomes minus 6. Here is minus 4. Y coordinate is not affected. Just now the coordinate 3, 5. So imagine now it becomes 9, 5. So this is x, y. Okay, so this is all about the thing on page 2. Okay, so before we move on to the next page, right, so maybe I can just put a few more things here, just additional information. Okay, I pull it up here. Just now here is until number 5, so I put number 6 over here. Number 6, odd functions. So what is odd function? Odd function is where f negative x equal to negative fx. So that means if you change the object x to negative x, it end up with the functions become negative fx. So what it mean by that? Let's say example, y equal to sine x, or maybe I put fx. I put fx equal to sine x. So I change the object to negative x. Then it will become sine negative x. And based on the trigonometrics formula, I know that it will become negative sine x. Okay, so this is where the functions become negative fx. Okay, so this is an odd function. So anything special about odd functions? Odd function, there are anti-symmetry on y-axis. Okay, so this is the properties of odd function. So I write down first, anti-symmetry on y-axis. So what's the meaning? Let's say, for example, I draw out the sine graph. So the sine graph is like this, and the other side of the y-axis will look anti-symmetry. So they are not symmetry, they are anti-symmetry. So they are like the other way around. So which is like this. So if you want to understand anti-symmetry, my suggestions, maybe you can just think like this. Symmetry is like the blue color one. Symmetry is like this. So anti-symmetry, you just turn the blue color graph upside down, or reflect the blue color graph about the x-intercept, and then you will get anti-symmetry, this one. Okay, so that is anti-symmetry. It happens to odd functions. Odd function. Okay, odd function. So one more example for odd functions. Let's say I can put f. Why they call odd? Of course, there are reasons, right? So let's say one more example for odd functions. Let's say I put fx equal to x cubed. So x cubed, odd power, you see, odd power, odd functions. Okay, now is this odd function or not? Of course, we can easily check it. I put negative x to it, negative x cubed, it will end up with negative x power 3. So this is an odd function because I get negative fx at the end. Okay, how's the graph? Anti-symmetry, like that. Okay, so how to understand anti-symmetry about y? It is like this. First, we know that this graph is going up in this way. So anti-symmetry is here. So how to take anti-symmetry? My suggestion, you do reflection about the y-axis first. When you reflect, it look like that. After you do reflection, then you turn it upside down. I mean you reflect about the x-axis. Then it become anti-symmetry. So odd function, anti-symmetry on y-axis. So since we have odd function, of course we have even function as well. Okay, so since I have limited space, I put even function here. Even function. Even function. So even functions, the formula is if you put negative to the x, then you will get fx. You won't get negative fx, you get fx instead. So let's say, for example, fx equal to cos x is an even function because if you put negative x to the x, based on trigonometry function, it will become cos x at the end. That is fx. We get back fx. Okay, so what is so special about even function here? So even function is symmetry about y-axis. Symmetry about y-axis. So let's look at the cos graph. So we know that the cos graph is like this. So the other way of on the left hand side of the y-axis, the graph is just like that also. So this is called symmetry. So the left hand side of the y-axis, the graph on the left hand side of the y-axis is symmetry with the graph on the right hand side of the y-axis. So this is symmetry. Okay, so another example of even function. Why is it even? Because even power. So fx equal to x squared. This is also an even function. If I put negative x to it, negative x I power to it, so I will get back x squared, and that means I will get back fx. So the graph of x squared, this is basic, it's like this. And you can easily see that there are symmetry about y-axis. Okay? So odd function and even function, these are the additional information for graph sketching. So what else? Maybe I add one more, piecewise function. Number 7, piecewise function. Piecewise function, what is that? Okay, just in short, piecewise function, they will give you something like this. Okay, something like this. They will give you fx, then it's equal to a particular function for a particular interval, and then after that it will equal to another functions for another interval. So that is piecewise function. So let's say for example equal to, okay, so you draw 2x minus 1 when x is more than or equal to half. We draw x squared minus 4 when x is less than half. This is piecewise function. So for different interval, we draw different function. Okay, and one more things to add here. Okay, how to sketch y equal to x to the power of n in general. So in general, if n is greater than 1, we sketch the graph in this way. When n is less than 1, when n is less than 1, of course here I have to put additional information. N is still positive, so it should be greater than 0. So n is greater than 0, so in that case the graph is like that. Okay, so this is some general technique in graph sketching. So I have to say that we are done for this second page. Okay, now let's look at the third page of the notes, composite function, basic concept for functions. So first of all, if you see 1a, right, so this one we discussed before. At that time I say that one-to-one relation is a relation for functions. So this is B. This is one-to-one relation, but this is not a function because object C has no image. Okay, so the conclusion is to become a function, first it must be one-to-one relation or many-to-one relation. The second condition is all objects must have one image. Object with no image make the functions fail to be defined. Now we look at number 2a. So this is an example of fx equal to x plus 3. So what we can see here, so the left hand side are the objects. So for example 1, you plus 3, x plus 3, right? So 1 plus 3 you get 4, 5 plus 3 you get 8, 6 plus 3 you get 9. And we look at b now. The second function, gx equal to x squared. So these are the objects. So the x, 4, you square it, 16, 5, you square it, 25, and so on. Now the third function, c, fx equal to square roots of x. 4, you square root, you get 2. 9, you square root, get 3. 16, you square root, you get 4. Okay, so this arrow diagram represents this hx. Now let's move on. The next part. The question is, draw out the arrow diagram for composite function g(f(x) and h(f(x). Hence, determine whether the composite function is defined and then give reason. Okay, now we look at the answer straight away. As you can see here, if we want to draw g(f(x), we have to draw the arrow diagram for f(x) first. g(f(x) is a composite function, and the composite function start from the function at the back followed by the function in front. We start from f(x), so f(x) 156, we actually copy back this arrow diagram on top here. You see the object are 156, then it maps to 489, right? So over here we have the same idea. 156 are the objects, it maps to 489. Okay, that maps to 489. Now after we draw function f, then we have to draw function g. Function g is based on this thing. The objects for function g are 4, 5, 6, 7, 8, 9. So we already have 4, 8, 9. So we have to add 5, 6, 7. Okay, so now we have all the objects of function g, and then we maps to function. We maps to the image of function g, which are all these. So where you have to square it, and you get all this. Okay, so why we want to draw the arrow diagram for the composite function g(f(x)? Okay, so let's see the note on the other side. We want to check whether it fulfill the definitions of a function or not. So first, all objects have one image. Is it true? Let's take a look. All objects has one image. Okay, so how to see? These are the object. This object, one image. This object, one image. This object, one image. These are the object also. This object, one image. 6, one image. 7, one image. 8, one image. 9, one image. So all objects have one image. Okay, so it fulfill the first conditions to be a functions. Number 2, as you can see here, 1-to-1 relation. Okay, is that 1-to-1 relation? Let's take a look again. Our composite function, the arrow diagram, you can see, yes, 1-to-1 relation. Okay, one object to one image for all the situations here. Okay, it fulfill the second conditions. So g(f(x) is defined, is valid. Okay, it's valid. Now part B. Okay, let's look at the range of f. The range of f is 489. So where we can see that the range of f, let's see the arrow diagram again. The range of f 4, 8, 9. Yes, these are the range of f, 4, 8, 9. From here, point to 4, point to 8, point to 9. So these 4, 8, 9 are the range of f. Okay, now let's continue. What else they mentioned here? Domains of g. Domains of g is 4, 5, 6, 7, 8, 9. Okay, 4, 5, 6, 7, 8, 9. As you can see, the arrow diagram again. So function g start from here. So these are the domains of function g, 4, 5, 6, 7, 8, 9. Okay, now what am I trying to put in the note is, I'm trying to show you that the range of f is subset to the domain of g. Okay, so why I have to show this? This is the way to check whether a composite function is defined or not. So if range of f is subset or equal to the domain of g, then g(f(x) is defined. Okay, so that means how? Okay, that means how are we going to take it? That means you look at this arrow diagram. So the first function, right? The range of the first function must be subset to the domain of the second function. So that is how we take it. The range of the first function must be subset or equal to the domain of the second function. Okay, so let's come back to here. A composite function, we start from the back. So this is called the first function, and this is called the second function. The range of the first function, range of the first function is subset or equal to the domain of the second function. So if they can fulfill this, then the composite function is defined. So you must be very quick in determine this thing. Okay, let's say we take a quick practice. A quick practice here. If I have hgx, so what is the conditions to make the composite function defined? Range of g subset or equal to domains of h. So you get the idea, no? Range of the first function. The first function is here, right? So range of the first function is subset or equal to the domain of the second function. Okay, so if they can fulfill this, then it is defined. Okay, now let's say another example. If I have khx, okay, in what situation the composite function is defined? Range of the first function is subset or equal to the domain of the second function. So if they can fulfill this, then the composite function is defined. Now we look at another example. This is hfx. hfx start from function f. So I draw function f first. Okay, I draw function f where I copy back this thing actually. Then I draw function h. Function h come later. So function h, I take 4 to 2, 9 to 3, 16 to 4. Okay, that is a problem. This one. This is the object with no image. So object 8 has no image. You know, all objects must have image in order to be a function. Composite function is also a function. Object must have image to make it a valid function. So it fails over here, no? It fails to satisfy that condition. It is one-to-one relation, so it's one-to-one, no problem. So, but it cannot fulfill all objects have one image. This condition, it cannot fulfill this. So because of that, hfx is undefined. Of course, checking arrow diagram is not very practical in exam, because in exams the fastest way to check is by using this way, checking the range and domain, whether they are subset to each other or not. So that's why here, let's check the range of the first function, range of f. 4, 8, 9, 16. The range of f. The domains of h is 4, 9, 16. Okay, so you can see that the range of f is not subset to domains of h. So because of that, hfx is undefined. So in conclusion, fgx is defined if the range of the first function gx is subset or equal to the domains of the second function, the fx. Okay, so we already know how to check whether a function is defined or not. So what else to be expected in exam? So just a list. Composite functions. We already discussed through how to check whether the function exists or not. So we need to know how to find composite function also. This one we learned before in the lower level, maybe in STPM. So I think you should learn before. Find composite function. and then you have to know how to find domain and range of composite function. So I just take a quick discussion on the second one. Okay, if you understand the arrow diagram as in here, so what we can say is a composite function is actually a function that maps in this way. Okay, in this way. So if you have a composite function of gf, that means it is mapping from the domains of f. Let me write down, to the range of g. So it is mapping in that way. It's a shortcut to map from domains of f to the range of g. Okay, so that means if you want to find for gfx, right? If you want to find the domains of gf, so you can just look at the domains of f. If you want to find the range of gf, then you can just find the range of g. Okay, so this is the domain and range part. And the third thing that we need to know, we already discussed conditions of existence. In what situations a composite function exists? So the condition we already discussed here. The range of the first function must be subset or equal to the domain of the second function. Okay, so we have done for this page. Okay, so I will do some highlights on a certain question here. So let's say the first questions. Find the natural domain and corresponding range of each of the following functions. Okay, so for example, fx equal to x squared. So what is the natural domain? Naturally, x can take any values. And because of that, the range of, the domains for function f, we write like this. There are all kind of numbers. We call it real numbers. The range, we have to sketch the graph. Imagine that y equal to, or fx equal to x squared. The graph is like this. Then to find the range, we check the lowest point to the highest point of the graph. So from here we know that our y is always more than or equal to 0. So because of that, the range of f is y more than or equal to 0. Okay, now let's say one more highlight here. We can't go through all the questions, so I just highlight one or two here. So C, let's say 1C, question 1C, fx equal to square roots of x minus 3. So what is the natural domain? We put it in this way. For square root, remember, everything in the square root must be positive. So everything in the square root, x minus 3, must be more than or equal to 0. So we get x more than or equal to 3. This is the domains of f. So domains of f, x such that x more than or equal to 3. So how about the range? So the best way to find the range is to sketch graph. So we already discussed how to sketch the graph of square roots of x minus 3. So let's take a quick discussion again on this. First, you may sketch the straight line of x minus 3, which is like this, where here is 3, here is minus 3. So this is y equal to x minus 3. Then after that, remember what I told you before, the graph that stays below of the x-axis will disappear. The graph that stays above of the x-axis will become a curve. So if the straight line is a straight line to the right, then it becomes a curve to the right. So that is the graph of, the red color graph here is the graph of square root of x minus 3. Of course, the green color graph is the straight line, y equal to x minus 3. Okay, let's say I label it. So the red graph is y equal to, okay, let's say the arrow may confuse. Okay, so this, okay, so this curve is y equal to square root of x minus 3. Okay, so to find the range, let's take a look. Our graph starts from, in terms of y, right? So our graph starts from here and go all the way up. Okay, so the range is hence, the range of f is hence y such that y more than or equal to 0. Okay, so now let's move on. Okay, so let's highlight one question here. Okay, now these questions. Determine the domain and range of the following functions. Okay, let's say A. So how to determine the domains? Like what I told you, the x minus 2 in the square root must be positive. Then we get x more than or equal to 2. This is the domain. The range, the best way to find the range is to sketch the graph. So how to sketch the graph? Okay, we sketch y equal to x minus 2. So let's say I use green color to sketch y equal to x minus 2. So where here is 2, here is minus 2. Okay, now it become a curve, like what we discussed before. The straight line will become a curve. So it will become like this. Okay, so this red graph is y equal to square root of x minus 2. Okay, now we have to use transformation. We have to use transformation if we have plus 3 at the end of the function. The whole graph will move up by 3 units. So now the graph start from here and go all the way up. Okay, so this graph is y equal to square root of x minus 2 plus 3. So we look for the range, right? So it starts from here and go all the way up. So because of that, the range of f is y such that y more than or equal to 3. Okay, so just highlight one question. Okay, let's say I highlight one more question on this page. So let's say I look at 3f. Okay, 3f. Okay, now these functions have 2 square root. So for each square root, the thing in the square root must be positive. So I get x more than or equal to 2 for the first square root. For the second square root, 4 minus x more than or equal to 0. So I get x less than or equal to 4. Okay, so if you have two inequalities here, then you have to find out the common regions of these two inequalities. Imagine that the first inequality, they say x is more than or equal to 2, that go all the way to the right. The second inequality, they say x less than or equal to 4, it goes all the way to the left. Okay, so these two inequalities accept here as the common acceptable values. So that means to make these two define at the same time, so we have to take value from 2 to 4. Okay, so what happens if you take value greater than 4? Like for example, you take 5. So this is acceptable, but this is not acceptable. So it will make the function undefined. So when they take value here, if you take value here, for example, you take 1, x equal to 1. So x equal to 1 make the first square root undefined because it's negative, but it makes the second square root defined. So overall, it make it undefined. So to make the whole function to be defined, so we have to take the common region 2 to 4. Okay, so because of that, the answer for these domains of domains are n, so x such that x is 2 to 4. Okay, so another quick highlight for question 4 here. By using the vertical line test, determine whether or not each of the following equation is a function. So how are we going to do this? First of all, you need to know functions are many to 1 or 1 to 1. Their relationship are many to 1 relation or 1 to 1 relation. Okay, what is meant by vertical line test here? So this vertical line test should work together with horizontal line. Okay, let's say I give you an example. Okay, let's say I have y equal to x squared. So what is the way to determine whether this is 1 to 1 or many to 1 or 1 to many or many to many relation? Okay, so the one of the way is to check horizontal line test followed by vertical line test. Okay, I start from horizontal line test. Horizontal line, you have to draw a horizontal line at the place where you can cut the most numbers of points. So I draw it here, I can cut it at 2 points. Okay, so don't draw at a place where you cannot cut, you don't draw it here, no intersection with the graph. So we don't draw it at a place where there is no intersection. So we draw it here and there are 2 intersections. Okay, so this horizontal line test represent the first part of the relation. Which means it will determine whether it's many or 1 at the first part. So if there is 1 intersection point, then it's 1 at the first part. If there are more than 1 intersection point, as in here, so it represents many for the first part of the relation. So this is many. Now the second part, we have to use vertical line test. The vertical line test, you have to draw a vertical line at the place that you can cut at the most number of times with the graph. So where? Let's say I use black color. So I can just draw anyway. I draw it here. Then I can cut the graph at 1 point. Then I can say that this vertical line determine the relation at the back. So if there is 1 intersection, that means the back is 1. If there is many intersection, which means more than 1 intersection, then the relation at the back is many. Okay, so for this case, the vertical line have 1 intersection with the graph, so this is 1 at the back. Okay, so the relation is 1 at the back. So overall, what can we say is this is a many to 1 relation. Many because of horizontal line test, 1 because of vertical line test. So many to 1 relation. And if you come back to this question, maybe you're wondering, how come they just want to use vertical line test? Okay, the reasons is here, no matter it is many to 1 or 1 to 1, right? The 1 at the back, right, is because of the vertical line test. The 1 at the back is the vertical line test. As long as the vertical line test intersect the graph at 1 point, then the relationship will be either many to 1 or 1 to 1. But if the I write down vertical line test. If a vertical line intersects at 1 point, then the relationship is 1 to 1 or many to 1. If the vertical lines intersects at more than 1 point, then the relationship is either 1 to many. It affects the back, right? So the back will become many already, or many to many. As you can see, the back will become many. So that's why vertical line alone can determine whether it is a function or not. Where if they intersect at 1 point, as you can see, they are functions. If they intersect at many points, then it will end up with 1 to many or many to many, so it is non-function. Okay, so let's take a look here. We do vertical line test. I will use black color. Okay, so this one, draw a vertical line, intersect at 1 point, so function. Draw a vertical line, intersect at many points, so this is non-function, because this is, in fact, this is many to many relation. B is many to many. Imagine if I draw a horizontal line, right? I have two intersections also. This is actually many to many, many to many relation, which is non-function. Okay, so the third one, if I draw a vertical line, intersect at 1 point, so this is function. So for this, if I draw a vertical line, I intersect at many points, so this is non-function. Non-function, non-function. Why? Because if I draw horizontal line, I realize it intersect at 1 point. So actually this is 1 to many relation, which is non-function. Okay. So page 7, nothing to highlight here. Let's move on. So just now we discussed about piecewise function, right? So these are the piecewise function. You can see, question 16. These are the piecewise function. Okay, so of course we can't go through every question here, so I will just leave it to you. Let's see. Okay, now let's look at the next page. So on page 9, okay, so on page 9, let's say we discuss one question here. Okay, so let's take a look on question 4. The function f and g are defined by fx equal to 1 over x minus 1 and gx equal to x cubed respectively. Determine the domain and the range of function f. Okay, so the domains for function f, so we can say that function f. Okay, for a fractions, you have to know that a fractions, the denominator cannot be 0. Denominator cannot be 0. If the denominator becomes 0, right, so it becomes 1 over 0, which is undefined. So because of that, x cannot equal to 1. So the domains of f, you can say x is the real number except 1. So this is the domains of f. Now to find the range, so we need to sketch the graph. Okay, so how to sketch the graph? This is reciprocal graph. So you know reciprocal graph is y equal to 1 over x. And during our discussion, right, they say that the graph is like this. But this is fx equal to 1 over x minus 1. So we discussed this also. When x minus with 1, it is a transformation to the right. So the graph will shift to the right and it look like this, where the vertical line is called, the vertical dotted line is called vertical asymptote. And from here we get to know that the range is all the value except 0, because the graph keep going up, the graph keep going up and keep going down, but they never touch 0. So when you write the range, so we can just write like this: range of f is y such that y are real number but y cannot equal to 0. Okay, now we look at part 2. Part 2, function g x cubed. Okay, so basically for x cubed, x can be any values. X can be any values, so all real numbers can be accepted, no matter it's positive value or negative value, you can just power 3 it. So the domains of G is x such that x are real numbers. Okay, then after that we sketch the graph of x cubed. So we realize that the graph is like this. So after we sketch the graph, then we can find out the range. So as you can see, the range, the graph go all the way up and go all the way down, and hence the range of G are all the real numbers. Okay, all the real numbers. So okay, that is A part 2. Okay, A part 2 have done. Now okay, let's move on. We look at 4b. Explain why GF exists. So remember, the conditions to make the composite function is the range of the first function, which is range of G, no, range of f. Our first function is G. Our first function is function f. The range of f, the range of f must be subset or equal to the domain of the second function. This is the condition. I put it in the box first. So let's see whether they can fulfill this or not. So I just write again. Our range of f are all the real number except 0. So this is the range of f. Our domains of G are basically all the real number. Okay, so you don't care about the y and the x here, you just look at the values. And we realize that the range of f, which are all the real number except 0, is part of these domains of G. Because domain of G can take everything, right? So this is the range of f is basically a part of it, a part of the domains of G. So range of G, range of f is subset or equal to domain of G, and hence GF exists. So that is how we answer the question. They focus on whether you managed to write this subset part or not. So if you manage to write it out, then you get marks from there. Okay, now let's move on. For C, find GF and determine its domain and range. Okay, so we find the composite function GF. Okay, composite function GF, let's say part C, I do it here. GFX means we substitute fx 1 over x minus 1 into gx, into x cubed. So we put 1 over x minus 1 into x cubed. So it will become like this, and this is the, okay, if I simplify it, then 1 over x minus 1 cubed. So this is called the rule of the composite function. And after that, determine its domain and range. So if you still remember the idea that we discussed just now, the arrow diagram. So basically, if you see the arrow diagram, right? So function f start first, followed by function g. So this whole thing, the shortcut is gf. Okay, so the domains of gf is actually the domains of f. And the domains of f, we just copy from what we have found just now, which is here, real number f set 1. Real number f set 1. Okay, so that is the domain. So they will share the same domain. So let's write down. Okay, so there are x such that x are real number f set 1. Okay, now the range. The range of GF, like what we discussed before, you look at the arrow diagram at the same time. The range is here because the composite function maps to here. This is at the same time the range of G. So the range of G we have found. Okay, let's see. This is the one. The range of G is here. They are real number. They are real number, and you have to be careful because we also need to check whether there is any x values that makes the function undefined. Okay, so how to check? We can't take the range of G straight away because there are certain values that make the function undefined. So let's look at it in this way. You look at the graph again. Remember our functions, our composite functions start from function f. So we look at function f first. Our function f, right? First, they cannot take 1. Okay, they cannot take 1. And then when they maps to the range cannot take 0. The range cannot take 0. Okay, so I try to put it here. This one cannot take 1. So when they maps until the middle part here, so what happens is that one cannot take 0. Cannot take 0. So if they cannot take 0, right, then function g, you look at function g. Function g is basically the x cubed, function g. Now your objects for function g, your object for function g cannot take 0. So they cannot take 0 now. Okay, so I put on the graph in blue color. I put a circle here. Okay, they cannot take 0. As you can see in the graph, they cannot take 0. If they cannot take 0, then when the object is 0, the image is 0. When the x is 0, the y is also 0 for this function g. So because of that, when they maps until here, this cannot take 0 as well. So because of that, we must be careful. The basic idea is the range of GF is the range of G, but we need to consider also the value that make the function undefined. We need to consider that also. Okay, so that's why we can't take real number straight away. They are all the real number except 0. Okay, because 0 is undefined beforehand. Okay, now the answer. The range of GF is not exactly the same with range of G, so I don't want to write that. I just write there are real number except 0. Okay, so let's move on. Next page. This is just answer. Move on. Answer. Answers. Okay, now we have the past year questions. So this past year question, let us see whether we want to go through any question or not as our highlight here. Okay, maybe, okay, so okay, I leave it to you. Let's move on.